you might know that I like to do things that don't seem like they make sense, but it's used for something else later. And so that's what I'm going to do today. I want to use this vector identity that looks really weird. It's like the curl of a function f. And then this is the divergence and the gradient of the divergence. And then that we haven't seen before. I haven't shown that before. That's the Laplacian. And so instead of deriving this, which I really don't like, instead I'm going to do a numerical calculation of curl, numerical calculation of divergence, numerical calculation of gradient, and the Laplacian, and show that both sides are true. And I already did part of this. I already did numerical calculation of curl, numerical calculation of divergence, numerical calculation of the gradient. And I'm going to briefly go over those. I'm going to use my functions to make this new function, because really the only new function I had to make, I have to make this as a new function and that as a new function. I need 3 new functions, but I can do it. We can all do it together. Okay, so let's start off with some basics. Suppose this f is some vector field, so it's some function of x, some x component of that depends on x, y, and z. A y component depends on x, y, and z, and the z component could possibly depend on x, y, and z. So here's an example: 3z squared xyz x squared z squared. And so I'm using this angle bracket notation for vectors. That's the x, y, and z components. And everything I'm doing is in Cartesian coordinates. If you want to do this in spherical coordinates, good luck. Okay, it gets a little bit more complicated, but we're going to stick in Cartesian coordinates. Next, we have this operator. I call it the Dell operator. People call it different things, but this is an operator, a vector operator. So it has a vector symbol over it because it has 3 components. And so as a vector, it would be the partial derivative with respect to x in the x component, the partial with respect to y in the y direction, and the partial with respect to z in the z direction. Now, the Laplacian, this is called the Laplacian right here. And this is normally, you would use this for a scalar function, because see, it gives you a scalar answer. We can do it on a vector. You'd have to do it on each individual component of the vector, and I'll show you how to do that. Okay, so let's start with this, the curl. I'm not going to do the curl of the curl, because if you do the curl, you can do the curl of the curl, right? That makes sense. Okay, so if I do the curl, I'm just going to write it out. I'm not going to actually take the curl of this function. I'm just going to show you what it is, and then all I need to do after that is show you how to take derivatives numerically. Okay, so the curl, if I do the cross product, if I do del cross f, I can find that by the determinant of the matrix x hat, y hat, z hat, and then the components of del, which is going to be partial with respect to x, partial with respect to y, partial with respect to z, and then my x components, which I'll just write as fx, fy, I always do my y's like a z, fz. So I have to take the determinant of this. If I expand about this row, I'll get an xy, x hat, y hat, z hat components, and you can get the determinant of that is the curl. And I'm not going to do that. Okay, I already did that, and there's another video on that down below somewhere. I have that video. Okay, so if I take the curl of f and I take the curl of f, that's okay. Now this is the divergence. So the divergence is pretty simple, because if I take del dot f, it's just the dot product. So if I take this vector dot that vector, I just get a scalar. I get the partial of fx with respect to x plus the partial of fy, see, I did it again, with respect to y, plus the partial of fz with respect to z. So that's that. It gives me a scalar function. And then finally, the gradient is if I take this and operate it on a scalar function, then let's just call the scalar function g. Let's call this g just for now, g of x, y, z. Then del g would just be a vector partial with respect to x of g, partial of g with respect to y in the y direction, and the partial of g with respect to z in the z direction. So that's that. Okay, so now just one more thing. What about this Laplacian on a vector? Let me write that out. Okay, so let's say I have del squared, and that's not a vector. Okay, f, that is a vector. So this is just going to be equal to, you can write this as del squared fx, del squared fy, del squared fz. So I take the Laplacian of all the components. And so if you wanted to write that out, I'll just write out this first one. Del squared fx would be the second partial of fx with respect to x plus the second partial of fx with respect to y plus the second partial of fx with respect to z. So all of these are just dealing with that fx component, but I take the derivative with respect to x, y, and z, the second partial with respect to x, y, and z. Now, so of course, if this doesn't have a z component, it gets a little boring. Okay, now, how do we do, just if I have some scalar function, all these things just deal with partial derivatives, okay, of a function that can change in the x, y, and z direction. So let's just say I want to do this. What's the partial of g with respect to x? I want to evaluate that at some particular point. Okay, I need to evaluate it at a point. I'm not going to calculate this everywhere. I'm calculating it at a particular point. So suppose I have this function g as a function of x, and it changes with x like that. And the partial derivative of this is the same as the slope if I'm only changing x. So what I want to do is I want to find, let's call this value x0. That's where I want to find the derivative at. And then I can move a little bit ahead and a little bit behind. So let's call this dx and then dx2. And then I have a new functions at this one right here is g of x0 plus dx. And this right here is g of x0 minus dx. And so I want to find the slope between those 2 points. So the slope, which is the partial of g with respect to x, is going to be equal to, I need to know this, I'm actually putting in a little number here for dx. I'm moving ahead, whatever value I want, we can change that. So this is going to be the change in the y values, which is going to be this minus this. So I get g of x0 plus dx minus g of x0 minus dx, and all of that divided by the horizontal distance, which is going to be 2 dx. In this case, 2 dx. So that's how I'm going to do my partial derivative. So I want to do the partial derivative of fx with respect to x. I would put this as the x component of the function, and the x component of the function I would change with x. If I want to do the partial of fx with respect to y, I'd use g as fx, but then I'd do these in the y direction. Okay. What if I want to take a second derivative? So if I want to take a second derivative, let's imagine I have some function g again, and I have, here's my main point, and then here's a point there, here's a point there. So this is going to be at x0, this is x0 plus dx, and this is x0 minus dx. So I have those points. So the second derivative of g with respect to x is the slope of the slope. So I need to find the slope. I'm going to find the slope right here. I'll call that g dot. So this is going to be the difference in slopes between those two. Well, for this slope, I can do something similar. I can use the change in just these 2 points. Instead of using one ahead and one behind, I'm going to do it in the middle point, right? Because then this distance right here is delta x. So the slope right there, based on this and that, is going to be equal to g0 of x plus dx minus g0, not g0, x0, g of x0, all that over dx, right? Because that's how far this is. And then I'm going to subtract off this slope, so it's minus g of this x0 minus g of x0 minus dx, all of that over dx. Those are my two slopes, and then I need to divide that by dx to get the rate of change of the slope. So this actually comes out pretty nice, because here I have, first of all, I have over dx squared, right? That's going to be an improper fraction, dx squared. And then I have g x0 plus dx. This is going to be a minus and a minus, so I get g x0 plus dx plus g x0 minus dx. And then I have a minus g x0, and then I can get another one, so I get minus 2 g x0. So I can calculate the second derivative just by adding and subtracting dx. And this is a second derivative with respect to x. If I want to do it with respect to y, all of this be y. Okay. I think we are ready. Okay, let me switch over to Python. There are some things I want to show you. Let's see, switch to computer. Hello, computer. So I already imported the stuff that I did before, because like I said, I already did this. So let me just make this a little bigger. Okay, I hope that's big enough. Okay, so let me just go through this. I'm going to give you the code. Don't worry about that. And look, I'm wearing a t-shirt. That's because it's Saturday. I wear t-shirts on Saturday, unless it's really cold, and then I don't. Okay, so I'm using GlowScript VPython web. Web VPython is the preferred name. Use web VPython. Let's all use web VPython. So the first is my function. I need to define my vector field, and it can mostly, it can't be anything, okay? Because if you have something that's not well behaved, that blows up at some point, things aren't going to work. But as long as you pick something that's, normal human level functions, you should be fine. So I'm using this 3z squared x. So this is a Python function. I give it the vector value rr, and then it returns another vector, and the z component of that vector is rr.z. Okay, so this is 3z squared x, y, z. Is that the one I wanted to use? Yeah, that is the one I said, right? Yeah. And then x squared, z squared. So it just returns that. I already put this in just because we're going to use it. This is the real Laplacian. If you actually go through and analytically find that Laplacian of that function, then it returns this. This is the vector value for that. Okay, so we can check, because I get nervous about some stuff. Okay, now I'm going to delete some of these functions. I just copied them over. So this is the divergence of f. Now, I like to do things that make sense, not the things that are the best. So there, I said it. So one of the things that I do in my functions is to use this other function up here. I didn't pass the function to this other function. I just have, this is actually a global function, which some people say you should never do that and you're a bad person for doing that. But, I know I'm bad. It's fine. I accept being bad, so it's okay. So what this does is it has some step size, which I call generic step size ds. So I can go in the same direction in all dimensions, and if I want to change it, I only have to change this one thing. Then dx, dy, dz are the steps in the x direction, the y direction, the z direction, and then what I do is to calculate the x component. Remember, this is the divergence of that vector field. I need to do the partial derivative of fx with respect to x. So here I have, right here is fx at x, well, the vector plus dx. Actually move it in the vector direction of x. But, everything could change. Y and z could change too, so it's important. And then that returns a vector, so I need just the x component of that. So that's what that dot is right there. And then I have minus the f minus delta x component, and then divide that by 2 ds. And I do the same thing for the y, do the same thing for z, and then I add all those together and return that scalar value, and that's the divergence. We don't use this. That was just for testing. I'm just going to delete that. We don't talk about that. We don't talk about Bruno. We don't talk about the curl analytical, because it's for another thing. So this is the actual curl, the numerical curl. So again, it just depends on first partial derivatives. But now you have things like this. Here's the z component of f, but you see I'm adding y and subtracting y. So this is the partial of fz with respect to y. That's what this whole thing is right there. Okay, and then right here, this is the partial of fy with respect to z. Okay, that gives me the x component of my curl function. I just call it cfx just temporarily. And I do the same thing in the y, do the same thing in the z, and then return x component, y component, z component, and I get a vector. Let's delete this. This is the analytical version. It was for a different problem of the divergence. This is a function g. I'll leave it in there because I don't really need it. Let's get rid of this. This is the analytical gradient of g. I don't need that. This is the gradient of g, right? So the gradient of g takes that scalar value g and takes a partial derivative with respect to x, y, and z and returns a function. I have that. Okay, so now we're ready. I'm looking at I want to verify both sides of that equation. So the first thing I need to do is take the curl of the curl. Okay, so let's take the curl of a curl. Let's make that as a function. Because the problem is that I can't just, I'm going to use my curl function. Okay. Yeah, let's just do it. Okay, so let's just say def curl curl. That would be funny. Curl curl f. And I'm going to give it some vector value that I pass into it rr. And then, so what I'm going to do is I'm going to use the same thing up here. I'm going to copy all that. Okay. Right, so that's that. So right now it just looks the same, but it's not the same because what I'm going to do is instead of, and what was I calling that? Curl f? Curl f. Okay, so right here, all I have to do, instead of using the function f, I'm going to use the function curl f. So I'm going to say curl f. I'll have to change these curl. Let's do this. This will be cool. Copy. And then I'm just going to paste this in front of it. So now I'm changing, instead of calling the f function, I'm calling the curl f function. Right? So I actually am taking the curl of all these things. And yes, I'm doing this. Maybe there's a better way to do it, but the way that you do it is the best way to do it. Yeah. So don't worry about. I mean, I think that was one of the things that I've seen people kind of hold them back with doing numerical calculations in physics. Like, well, that's not the best. That's not the way a computer scientist would do it. Don't worry about that. Do it the way you would do it. And I did this before. I'm thinking that might not work. It might not work, but let's just see. Let's just try. I don't know what the curl of f is, but let's print out. Let's pick a vector value. Let's just run this as a test. You don't want to get too far before things go bad. So I'm going to say r temp equals vector. Let's say 1, 2, 3. And let's print curl f equals, and let's say curl f r temp. And let's just see if it runs. If it gives me an error, then there's definitely a problem. If it runs, there could be a problem or there might not be a problem. Okay, so it gave me something weird. That's fine. Okay. This is, you know what this is? 10 to the negative 10th? 0. I mean, it's essentially 0. Okay. Okay. So I guess that works. Let me see. I actually did do this before. Let me just double check that I got the same thing. Yeah, that's what I did. Okay, so now I'm looking over here. I got that. Now I need the gradient of the divergence, and I'm going to make that as another program too, another function. So let's call that def. I'm going to call it's the gradient of the grad div f rr. So I need to give it a pass it a vector, and it's going to take the divergence and then take the gradient. So I already have the divergence function. I just need to take the gradient of that. So let's go up here to this gradient of g. I'm going to copy that. And you probably see what's going to happen, right? First, I'm going to fix that indentation error. And then how do I call that? Div, what do I call it? Div f. Okay, so instead of using g and all these things, I'm just going to use div f. So div f. Is that what I called it, or did I call it capital div? No, that's right. Okay, div f. So I'm just going to replace those. I'm not even going to replace these gx's over here because I don't really care. I was going to replace this div f. This div f. This div f. And you have to say it out loud, div f. You have to. You're required, div f. Okay, so that should work. Let's do this. Print grad div f equals grad, I put the capital div f r temp. If it runs, I think we'll go ahead. Again, it could be wrong. Okay, so it gave me a vector value. That's what I was expecting. I was expecting a vector value, so that's good. Okay, so now we need the Laplacian. So I could make a new function called Laplacian, but I think it's going to do this all at once. Okay, and in fact, I might even cheat because I actually did this. Let's call this def VLAP of RR, because it's the vector Laplacian, right? It gives me a vector value using my function that I defined up above. Okay, so I just want to point that out. That's the thing that I'm using. Okay, so let's just copy. I'm going to use this stuff too. Copy that. And then go down here. Now, the thing here is I need to take a second derivative, right? I'm taking the second derivative. So the first thing we want to do is define the x component of the Laplacian. So let's call this L F T X. So this is temporary Laplacian. It's the Laplacian of Fx. And that gives me the x component of this vector Laplacian. So that's just going to be equal to the second partial of Fx with respect to x plus the second partial of Fx with respect to y plus the second partial of Fz with respect to y to x to z. Yeah, it's x, y, z. Okay, so let me just start off. What we're going to do is take the partial derivative of f with respect to x, fx with respect to x. I know it's confusing. So remember I said the partial derivative is going to be f of rr plus, this is the x component, right? So it's going to be dot x plus frr minus dx dot x minus 2 times frr dot x. Right, they're all x components. And then I'm going to divide that by dx squared. See, is that right? I'm going to call it, no, dx is a vector, so ds is the step size. That way I don't take the magnitude. So this is the partial of fx with respect to x, right? The second partial. Now I need to do that in the partial of fx with respect to y. So it's going to be the same thing plus, it's going to be the same thing except it's going to be dot x, right? These are all dot x's. But these are going to be y. I'm going to move it in the y direction. I'm going to move this one in the y direction. But it's still x. Checking. Yep. And then I'm going to do the same thing in the z direction. Oops. So I say plus, copy that, and then change these to the dx to dz. And that's it. Okay, and that's the x component. Now, I just need to do that in the for the y. Okay, so now I'm going to call this fix indentation LTFY. So all I need to do is change these dot x's to dot y's. Other than that, it should work. I think, I always get a little scared. A little scared of doing this, right? Because you make some silly mistakes and you feel dumb. But if it works, then it works. And then I'm going to be happy. Oops, did I finish that one? No, I didn't. Y. Now I have to do the exact same thing for Z. So I'm going to paste it. Fix the indentation. Change that to Z. And then change all these to Z. 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 Just 3 more, I think. Z. Z. And finally, Z. Okay. Now, I'm going to return the vector LFTX, LFTY, LFTZ. Now we can check this. So let's say I already have our temp right down there. Let's do this. Print Laplacian equals of F equals, and let's call this VLAP RTemp. Now, remember I said I did it up here analytically. So I call it real Laplacian. Let's also print that out. Print real Laplacian F. And what do I call that? Real Laplacian of RTemp. And I'm putting in RTemp because I've already assumed F. Let's see if this works. I don't know. I really don't know. I should save it. I should save it. Save. I'm not a big saver. Okay, so we're not done. Hold on. Don't celebrate too long. But see, look. 6, 0, 20, 6, 0, 20. I mean, bam. Right? Bam. Okay, so now let's calculate that vector identity. I'll just leave this stuff up here because why should I delete anything? Never delete. And what I'm going to do is I'm going to calculate the left-hand side and I calculate the right-hand side. I don't know why that's like that. Okay, so let's call this left-hand side equals. And it is the curl of the curl. So it's going to be curl F, O-F, R temp. And then the right-hand side is going to be equal to the grad div F R temp minus VLAP R temp. And then let's say print left hand, let's just print it out. Left hand side, and let's put equals, which is a bold move, I know, equals right hand side. Let's see if they have the same thing. Okay, 9, 0, negative. That's winning, right? So definitely the negative 17 and the 9 are good. The other one is good too because that's 0, right? Because we're doing a numerical derivative. We're moving it a little bit to the side, so it can give us a little bit of weird result. But come on, 10 to the negative 10th, or 2 to the negative 10th times 10 to the negative 10th. That's 0. Okay, so we can do a couple things here. I do kind of want to make one. I was going to make a graph of the x component of the left-hand side versus the x component of the right-hand side, but I don't think I'm going to do that. Here, let's go up here and change our function because I had a different function. Here's x squared y, 2xz, and then have z squared minus 2y. So let's just change that. I'll have to uncomment this one and comment that one, and it should still work. It'll give me a different value because it's a different function, but it should still work. Okay, so I got 0 to 0 and 0 to 0. I mean, right, that's 0, right? You're okay with that being 0. We're okay. Okay. Save. I'm pretty happy. I mean, I would like to make that graph, but I don't want to make the graph because it's already a 27-minute video. And I mean, how many of you are actually going to make it all the way to the end here? You can make the graph as a homework. I think that'd be a great homework assignment for you. I'll give you the code here. You can play with this. And like I said, I'm going to use this vector identity. You probably know what I'm going to use this vector identity for. And if you don't, I'm going to make another video on that soon. So, all right.